I've been hours and hours looking for more explanations about a density matrix, because I so let me show you. Why? So my question is why do why does this why is this even displayed here at all, right? So I get if you check out the other videos, I get it that it's another way of representing the state in a way that the diagonal elements are equivalent to the probabilities of that particular state being measured, in this case 0 1 0. But what's curious is about the other ones, and I realized that some papers they use the matrix. I don't know. I had in the second video, in the second part about of the density matrix series, I had this feeling where I thought maybe this is a way that we can sort of understand what's going to happen when we're using the Hadamard gate, because if you pay attention to, like, as I add Hadamard gates, the space gets filled up. So, but at a certain point when you then start adding Hadamards again, the space gets empty again, right? So I'm really trying to understand that without the maths behind this. I've read some of the maths on how this is constructed and whatnot, and sure, it makes sense, but I was intuitively, what is this useful for intuitively, right? So what does those things mean? So this is one thing. So if you pay attention when you do something like that, which is the way that in Grover's algorithm we flag the item 111. So then you've got this pretty nice, where you kind of see that there is something here, right? Which is, and then so kind of indicates that that's negative, maybe, I don't know. And then there's like a complex version or a complex part of this, which it seems to be empty for most of the time. So I'm trying to figure this out, and then I just came across a couple of interesting explanations, which I want to kind of reread, make sure that I understand them well. And I know that probably there's thousands of different interpretations of what this matrix is, but I want to get that one that is helpful for the quantum programmer, for the person that's building. Why is that helpful? If I'm building a circuit, why is that helpful to me, right? Good, I can understand maybe it's a way to store a state, but it's also, yeah, so let's see. Let's see. Oh, also, if you do something like that, right? Because I have the suspicion this might even be useful to understand whether when there's like entanglement, or maybe to understand the correlation. Because in this case, there's no kind of there's no correlation, right? So it's like everything is like has those values. You have equal values. But as soon as I do this, which is I'm building this basic this basic correlation thingy. And now it gets interesting, right? Because now those values are empty, but the edges are filled up, which is the 1100 and 0011. Which maybe this is a tool to help you understand that that's how they correlate. This means that it's telling you it's going to be 00 or 11 50% of the time. Which kind of you can, in this simple case, you can understand from just looking at this one, this here. But so it kind of means they agree, right? Always. I don't know, maybe. So and I came across this explanation here, which is so there's something interesting here, because it says if in that sense we can take this and read the two probabilities off of it. They'll tell us those probabilities for the x and the y axis of the Bloch sphere, whereas p and r tell us about the z axis. So p and r are the diagonal items, and then these other q. So q has a real and a complex component, and I think that's how the IBM Q guys split those two matrices. But does this mean that Does this mean that so in the state basis, the real part of the off-diagonal elements contributes to the occupancy of the plus-minus states? In the majority component contains information regarding the phase relationship between the two states. This is one interesting thing. And what I have in my mind right now, it just came, can a correlation matrix be regarded as a quantum density matrix? What's the short answer? No mass. So yes. So it seems like it can be that those elements represent the correlations, which that would be pretty cool. And it just came to my mind. Maybe, let's see. Maybe there's a relationship between. There's a relationship maybe between the density matrix and what what is in the Hello Quantum game. Where have I gotten that? I think IBM. That's because James Woodon was super nice, sharing with me. No, not this. Qiski Quantum. Maybe I gotta check Twitter because he shared with me the link of a new version. And so I got the notifications, and I think he basically blah blah blah. Oh yeah, here you have it. Hello Qiskit. So maybe this is to some extent maybe there's a relationship between these and then the that would be awesome, man. That would be pretty cool. So it basically means this is telling us about it's telling us, and I'm sure it can be used for many other things. And I'm sure that a lot of people are like, no, it's not just this, it's this and that and blah blah. But because here, what we were seeing in this game was that first of all, so you keep track, you're keeping in the game track of 2 dimensions. So this is the Z measurement, if I remember well, and then this was another measurement. Was it on the after applying a Hadamard, which would mean in block sphere terms the x-axis? And sorry if I have to get a bit technical here, but I think that's what it meant. And then they were introducing yet another measurement, which was on the on applying an S or something like that. And I think that probably is the y-axis, which is, oh my god, what have I done? Which is at the end of the day what these people are saying here, what this person is saying here is saying you can read out those probabilities. Interesting. How could we check that? So in the IBM biz IBM. So here, because there's a Medium article, interesting quantum circuits. What's this one? Where Wooden does an awesome job. No, that's the Q experience for us. Yeah, so that's a Q experience. No, I'm looking for Hello Quantum, or no, I'm looking for James Wooden, how to visualize 2 qubits. I remember there was a really good article. Is this one? Oh, come on. I haven't read this one, I think. Oh, come on. Where was that? Part 1. No, that's not what I'm looking for. That's not what I'm looking for. I'm looking for Can I just take a look at these articles in Medium, maybe? How to program quantum computer. Dia's computation. Oh, maybe maybe this one. Maybe this one. Because I think he explained exactly. So he explained here how to make the puzzles. Okay, yeah. So maybe let's try to make that. Let's try to make that thing here. So that was a Control Z. So oh, so we got links to the puzzles. Okay, that would be cool. What I'm trying to do. I'm trying to find a puzzle and then trying to see if I can compare the way this matrix looks like with the way the density matrix looks like, just to get a sense of whether those things are sort of equivalent, or because I remember in the game it's mentioned that this is all you need to really represent the system of in this case the two quantum states, and then so this is what puzzle this is. Level 4 puzzle 1. Level 1, level 2, level 3, level 4 puzzle 1. If I click on that, what happens? That's going to the old version of it. Blah. Cool. Okay. Let's see what we get. Let's see. It doesn't look like it's opening. Then let me go back to this and just try to do this. I think what the trick here was target center work. I think that was this and this and this. Yeah, so was okay. Let's do this. So let's take this. Let's take 2 qubits. Maybe I'm going to even put it on the side and then choose this. So oh no, that's not a good idea. That's not a good idea. So let's keep it at 2 qubits. And so what they do is so what he does is 2 Hadamards, then a Z, and then a Control Z. So this gives us the following state vector, and this gives us the following density matrix. Now let's try to understand and see how this compares to that. Wait a second. So this is what we're trying to get, right? Where we've got full uncertainty on the Z basis, and this is exactly what we see here. It's full uncertainty. So on the Z basis we don't know. It's all over the place. It's actually pure, right? It's not even like a little bit this. Is okay. So that matches. So this is this exactly. On this basis, so this here is this is what you would measure on the x-axis, and it's also uncertain, which it also matches here because all this is filled up with equal values, even though they're positive and negative. I think that's the correct way of reasoning. So you see there's no special imbalance or whatever, and that's just I think we can just ignore half of the matrix, and here there's nothing going on. So okay, and so if we take a look at so and then we say here, okay, so I think if I remember well, this means this black here meant that this black here so I don't know if I'm actually reasoning this from the right perspective. because, so let's we'll set up the initial state of level 4. This is what it is to first make the target state and then work backwards to the initial state. Okay, yeah. So we're talking about the initial state. Sorry, I just want to make sure that I was not talking about this thing here. So that's correct. And so this, I think this being black meant that they would always disagree. No, agree. I think off was agree and on was disagree. So this black here meant that the Z, and so it's a bit more tricky to understand, right? Because here we've got the two qubits. So the 2 qubits we've got here. 2 qubits, and here in the matrix is a bit different because the 2 qubits are all the time like here, right? So 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 1, 1. Trying to figure out what does this mean that this is negative and that this is positive. It means they're positively correlated, negatively correlated. But what does this really mean? So we're talking about so if I understand well the actual fact, so because it's not a direct mapping, okay? So we're not trying to, it's not that these maps to the diagonal items, not at all. I would rather say the non-diagonal items kind of basically, there's this understanding here, right? It's just that this information of agreeing or disagreeing is what I'm trying to find out, because so maybe if we take a look at so this is, let's say this is qubit 1 and this is qubit 2. So this is qubit 1 and this is qubit 2. And so this circle here is, this is a diagonal one and this is a non-diagonal one, right? So if I take a look at the diagonal one, so this means that for each diagonal one, right? If I take a look at a non-diagonal, seems to tell me, but I think I'm on the right. I think I'm on the right track. I think that's definitely the right way to see it. So the density matrix basically is helping us to understand the correlation, the way those things are correlated. That's really cool. I mean, I'm not so sure what's the practical usage of it, aside from basically having insight on the correlations, and then maybe that can help you understand how measurement is going to work out. And maybe that's useful for a bigger amount of qubits, right? Because for 2 qubits, it's kind of easy, right? You can say, oh, they'll always agree, disagree, or whatever. You can easily express that. But for a bigger amount of qubits, that probably is close to impossible. And also, the usage of that is probably more at the algorithmic level when you maybe want to do something non-quantum. So, because I'm at the same time taking a look at the quantum GAN concept, and I realized that the density matrix is used there to actually as an actual basis for the learning. So, and maybe that's because the way those correlations, that kind of defines maybe a bit of the shape. It's kind of your model to some extent, right? This is to some extent like could be used as a model for whatever AI stuff. And I know because I've read somewhere that there's no one-to-one matching between that and the actual vector state. So the actual how you got like the actual state, which is good. I'm not sure exactly why, but I think that's only if I could just figure out. So here's, let's say they agree. So what happens? I'm trying to see what happens, and these they will agree. So always the diagonal of the second diagonal element of the second qubit will always agree. Okay, so the diagonal element, let's say, so these are the diagonal elements, and the second qubit is 0 1 0 1. Yeah, so it's kind of 0 1 0 1. So if you take a look at just 0 1, let's forget about the rest of them. Let me clear that out. So now we're focusing just on this. It means, in this case, that, so it's red, negatively correlated. Could this mean that they, in this case, they disagree? And because it's a negative correlation, so this means when one grows, the other decreases, I guess. I don't know. Not really. I'm not really in shape with that type of language. And so here, and the other one is basically the diagonal elements of the first qubit and the non-diagonal of the second. So, and then the other one would be diagonal elements of the first qubit. That's trickier to understand, right? Because we've got 0 0 1 1. Okay, but then so if I take the second qubit in here, I think for each pair, okay, maybe that's another way of reading this. So I think for each pair of states that we have to read. So for example, for this one, 0 0 1 1, it's positive. Here we have 0 1. So when they agree, I feel I'm almost there. For 0 0 and 0 1. So here it's like, okay, so here we've got for the qubit 0, it's 0 1, and that's telling us 0 1 1 0 0 1 0 0 1 1. Okay, 0 1. Trying to read the other diagonal, so to say. So because from this perspective we've got 0 0. So as qubit 0, we've got here 0 1. Here we've got 1 0. Here we've got 0 1 again. And maybe the sum of those, so it's overall negative. So it means that they will Mhm. Negative. And here, there has to be a way to read that, and I'm gonna figure this out. I'm definitely gonna figure this out. I think this is. I gotta figure this out because I think that's it. I think that's it. I just need a way to translate that. Because also you've got these uncertainties here, right? Which means that this and this, so um, the non-diagonal will be it's tricky. Hmm. How can we read that? How else can we read that? The correlation between states 0, 0 and 0, 1. Is negative. The correlations between the states 0, 1, 1, 0 is negative. Measuring 0, 0 or 0, 1. Measuring 0, 1 or 1, 0. Measuring 1, 0, 1, 1. And this is positive. What does it mean? This correlation is positive. 0, 1. 0, 1, 0, 1. Because what this is saying is they will always when it's on is disagree, and when it's off is agree. So if we measure the qubit 2, if we measure the qubit 2 on the like z basis, and so the normal measurement, and we measure the qubit 1 on the x basis, they're always going to agree. They're always going to agree. That's what I'm trying to see here. That I don't know if the disagreement has to do with a sign here, but it could be. And so where we have the positive ones in 0, 0, 0, 1, no, 0, 0, 1, 0, 0, 0, 1, 1. So 0, 0, 1, 0, 0, 0, 1, 1, and 1, 0, 1, 1. So those are positive, and those are negative here. There must be a way to read this. There must be a way to read this. I'll give it another round. There's probably going to be another part, but I think that's definitely there has to be. I'm just not seeing it right now, but there has to be a way to read this, and I sense this is exactly what the intuitively what this can be used for, so you can understand what's the shape of the correlation, and I think that's super powerful because then you can understand more complex stuff, right? So this is a really simple one, but I guess you can get at the point where those values are not always the same, and so then it's not really a balanced correlation. And I think that's pretty interesting. Cool.